Okay, so this time I want to get more deeply into the idea of projections from conics to conics. So we're going to define things more rigorously, and then we're going to have a look at some specific examples which make Pascal's mysterious hexagon theorem and Pappus's ancient results seem a little bit less mysterious. I think it's going to be helpful if we recall the most fundamental definitions in projective geometry. So, namely, the idea of a perspectivity, and sort of below that is another concept which is fairly useful. Well, two concepts actually. The idea of a range, so the range of a line, for example, would be the set of all points on that line. Here I'm just showing two of them, but we can imagine a whole continuum of points on that line. And we can also speak about the range of a conic. So, say for example, we have a parabola, so I'll draw a few things like this. So here's a parabola, and again we can think of this as a collection of points, or at least we can speak about the set of all points of this parabola. Okay. So that's the range. The range of a line or conic is the set of all points upon it. The other definition is the idea of a pencil. So the pencil of a point is just the set of all lines which pass through that point. The pencil of a conic is the set of all lines which meet that conic tangentially. So the pencil of this particular conic, for example, is just the set of all lines which are tangential to this conic, this circle. And one can imagine similar things for the other kinds of conics, the ellipses and hyperbola, etc. Okay, so given all these ideas, how can we widen our notion of projections and perspectivities to include conics in a rigorous way? Here's probably the simplest kind of perspectivity, where you're basically doing a perspective from a set of points on a line to a set of points on a line. Now, essentially what we have here is a sequence of points, members of a range of this blue line, and another sequence of points, members of the range of this black line. And this is a perspectivity from this yellow point here, which can be called the origin or center or viewpoint of a perspectivity. Anyway, the important thing is that the reason why we say that this is a perspectivity is that for each of these pair of corresponding points, we can find a line through them that passes through this yellow point. A more sort of sophisticated way to say it would be that the ranges of these two lines are put into, well, the ranges of these two lines, which are basically sets of points, they're put into one-to-one correspondence in such a way that when one point in one range of one line corresponds with another point in a range of another line, then if you take those 2 points, let's say point A in the blue line and point B in the black line, well, if you look at the line AB, then that's going to be a member of the pencil of this center of perspective, this yellow point. So in other words, say we have a point A on the blue line and a point B on the black line. Well, the line AB should be a unique member of the pencil of this center point of a perspective. And in fact, we really have a perspective from a whole line of points to a whole line of points, although I'm only showing 3 points here and 3 points here. It's quite difficult to draw the continuum. Okay, so that's the perspective essentially from one line to another, or say from a range to another range, or say from a set of points to a set of points. Now the dual idea of this, something we've already encountered as well, is the idea of a perspectivity not from a set of points to a set of points, but from a set of lines to a set of lines. Okay, so now I'm going to talk about the dual concept, but before I do, let's just recap. I previously talked about a perspective from a blue line to a black line using a yellow point. So now I'm going to talk about the dual idea, which is a perspective from a blue point to a black point using a yellow line, called the axis of perspectivity. So basically the idea is that you have a sequence of lines exuding out of the blue point, members of the pencil of the blue point if you like, and each member of this sequence has a corresponding member of the sequence of lines going through the black point, and a given blue line is going to meet the line it corresponds to in this sequence at a place on the yellow line. So we could number these lines. Let's say we're going down from the top, so we'll number the blue lines: blue 1, blue 2, blue 3, and the black lines: black 1, black 2, black 3. Well, blue 1 corresponds to black 1, and they both meet at a special place on this yellow line. Blue 2 corresponds to black 2, they both meet at a special place on this yellow line, etc. So the sort of official, well, technical way to say it is that 2 points will be in perspective with each other when there is a one-to-one mapping or a correspondence, let's say, from the set of, from the pencil of lines of one point to the pencil of lines of the other point, such that when one line corresponds with another line, let's say when when blue eye corresponds to black eye, that means that the intersection of those two lines is going to be a unique point on the range of the axis of perspectivity, which in this case is the yellow line. So there's quite a lot going on here. If you think about it in a continuous way, we've got these points, they've each got these pencils of lines, infinite number of blue lines through this blue point, similar with the black point, and then we're putting these two sets in one-to-one correspondence to each other, and we're doing it in such a way that we can get corresponding members of this sequence. So one blue line from here, one black line through here, and they're gonna meet at a specific place on the yellow line. So in a way, this particular corresponding pair of lines is going to match up with a particular member of the range of this axis of perspectivity. And it might be helpful if you rewind a video and compare and contrast this description with the other perspectivity idea, because this is perspectivity from sets of lines to sets of lines, but it's almost completely analogous conceptually to the previous kind of perspectivity, the dual. Okay, so here now then is our notion of perspectivity between a line and a conic. So in particular between the range of a line and the range of a conic. So What we're doing here, I've just done it with a sequence of 3 points, but we could think of it using the entire range of points on both of these objects. But basically, we're putting these points in these sequences in one-to-one correspondence, and when they correspond with each other, that means the line through them goes through this center of perspectivity. And in the case with a perspectivity from the range of a line to the range of a conic, we insist that the center of perspectivity is a point of the conic, but not a point of a line. Okay, so this is the basic idea of perspectivity from the range of a point to the range of a conic. Finally, we have here a perspectivity from the pencil of a blue point to the pencil of a black conic, this circle here. So the pencil of a black conic is the set of all lines which are tangential to it. And this is a perspectivity via this yellow line here, which can be called the axis of perspectivity. So the story is actually pretty similar to before. We insist that the axis of perspectivity be a member of the pencil of the conic. Okay, so the pencil of the conic is the set of all lines tangential to it, and so we choose one of those to be this axis of perspectivity, and then we have all these lines of this conic, and basically we are going to put those in correspondence with these lines of our point, members of the pencil of the blue point. So we put them in one-to-one correspondence so that lines which are in correspondence with each other meet on this yellow axis line. And so basically now we've got the idea of perspectivity under our belts. The idea of projection is really quite trivial. A projection is nothing more than a sequence of perspectivities. So we could say that this circle here is so here we have a projection from the range of this circle to the range of this parabola. So let's see how this works exactly. Well, we have one perspective from the circle to this blue line, using this yellow point as a center, and then we have another perspective from this blue line, this range of this blue line, to the range of this parabola, using this orange point as a perspective. So a sequence of perspectives corresponds to a projection. So we can think of projections from ranges of conics onto ranges of conics, or onto ranges of lines, and we can think of projections from pencils of conics to pencils of conics, or to pencils of points. Okay, so let's have a look at this configuration here, where we have 3 pairs of points on a conic. We'll use a circle for simplicity. So we have one pair which is a light blue and dark blue point, we have a light red and dark red point, and a grey and a black point. There are 3 pairs. And let's just have a look at what kinds of constructions we can do here, because it turns out we can pull out some interesting relationships with things like Pascal's theorem by looking at some projections of this conic to itself. So firstly, is it possible to do a projection of this conic to itself which sends 3 points, let's say the dark blue one, the red blue one, and the black one, to the corresponding points light blue, light red, grey? Well, yes it is. So one fairly sort of brute force way to do it is just to say, well, we can use a center of perspective here, and a centre of perspective here. And we can map the dark points onto this dotted line, and we can map the light coloured points onto this dot dashed line. So you see what we're doing here is basically we're using this yellow point to send these the dark coloured points onto this line on the left, and we're using this orange point to map these light coloured points onto this dot dashed line on the right. So now we've got these two lines, each of which have 3 points on, and we can then construct a projection from one line to the other, which put our required points in correspondence. I showed how to do that in, I think it was Projective Geometry 5? Axioms, Duality and Projections? I think it was that one. So basically, you can always, given 2 lines, each of which have 3 points on, you can always make a projection so that you send the points you want, so that you can put the points in the kind of correspondence that you want to. So that basically shows, if we just go back, that shows that it's possible to do a projection of the circle to itself which matches up these points according to their colours. But let's now have a look at something else. What about if we draw some lines on this circle? Sort of like in Pappus's theorem. Well, if we do this, we've essentially drawn a kind of hexagram, or hexagon if you like, 6 lines, and we've essentially put these points in a kind of ordering by drawing the 6 lines. So we could think of the lines as adjacent if they're linked by a green line, or green line segments, should I say. Anyway, the point here though is that there's something kind of interesting, which is that if we now take a pair of points which correspond with each other, like say the red and the pink one, well, we can use those as projecting points or centres of perspective to actually make a projection from the other 2 point pair. Okay, so what we're going to do here is we're going to use the red point as our first centre of perspective, and we're going to use this as our kind of intermediate or auxiliary line, and then we're going to use this orange point as our second point of perspective. And let's have a look at what kinds of effects these things have on our other 4 points. Well, when we do the first perspective, that's going to send this light blue point to this purple line. Excuse me. And this grey point to this purple line. And now when we do our second perspective, using the orange point, that's going to get us so that the grey point gets mapped to the black point, and the blue point gets mapped to the light blue point gets mapped to the dark blue point. And the astute amongst you will have probably noticed that this line is nothing less than Pascal's line of the hexagon. So it's quite remarkable that this line from Pascal's famous theorem appears here. And also we can see, since this works for all conics, we can see that this is very closely related to Pappus's theorem. So I've drawn this on a circle, but it would work if I'd drawn it on an ellipse. And if we stretch out the ellipse horizontally, so it's very, very long and thin, essentially it would look like we'd have 2 lines, and then basically this would transform the configuration into Pappus's configuration. So we see that really this is Pappus's line appearing as well. So it's interesting to view this projection from the circle to itself using these light and dark red points just as a proper projection. So to do this, I've made this brown triangle to represent an object, and this brown arrow points to its image under the projection. And so we see that, of course, these places where this intermediate line crosses the circle, they're going to be the fixed points of this projection. And also it's interesting to note that the orange point gets projected to the yellow point, and if we look at the yellow point, we see that the projection seems to go off to infinity. And I think if this program was working properly, this would also send us back to the orange point.